record the video. It's good to record the video rather than nothing. So here we have some example, some formula here. This is one way to calculate, but it's not realistic. And then, but the useful formulas to calculate the matrix norm, matrix natural norm here. And so I just give you two examples. The A infinity norm. This is a useful one. So you don't need to take a look at that one, the maximum things. The things you need to use in this class is the following formulas. So for the one norm, and then for the infinity norm, we are going to take the maximum. And then this one is the I row. So for each row, you are going to calculate the sigma sum of the, so you are going to calculate the sum of the absolute value in that row. And then for each row, and then you calculate the row sum of the sum of the row element, absolute value. And then after you calculate that absolute value sum, and then you compare each row compare all the rows result, and then you take the maximum. This is for the infinity norm. And then what about for the one norm? And then for the one norm, you are doing the opposite things. You will calculate the sum of the column. So here I equals to 1, and then Aij, and then you're taking the maximums among all this column. Does it make sense? So this is not easy to see it here in this column, in this formula, but I will give you some examples to do it. Let's say we have this example 5 here. Example 5. This is just example for the knobs. And I'm going to give you the matrix, and then this is 1, 2, -1, 0, 3, -1, and then 5, -1, and then 1. And let's calculate the A infinity norm first. So first, you would get the for the first row. And then for the first row, we get this. We got the sum of the absolute value, the sum of the absolute value of the components. And so for the first row, we got this is 1 plus 2, and then plus the -1. And this is just 4. And for the second row, and then that is the sum of the absolute value for the second row, and then we got 4 as well. And let's get the third row. The sum of the absolute value. Sum of the absolute value. Don't forget the absolute value sign, and then this is 7. Which means that the A infinity norm is taking the maximums among all this number, the sum here. And then that is 4, 4, 7. And your maximum now of the matrix, infinity norm of the A matrix is just the 7. It's just equals to 7. And this is the A infinity norm. And then now let's take a look at the A1 norm. A1 norm, we can focus on the column instead of the row directions. We focus on column directions. So for example, here we need to calculate the first column, and then but we are counting the same things, the sum of the absolute value of the element. And then that is 6. And then for the second column, and that's the 2, and then plus the 3, and plus the -1. And we got 6. And for the third row of third column, and then we have the 1, and then plus the -1 absolute value, and plus the 1, and then it's equals to 3. And which means that the A1 norm is the maximum among this number, 663. That's the number we have here, the sum here. At the end, our mass, the L1 norm is just equals to L1 norm. It's just equals to 6. Does that make sense? So one thing you can do some memorizations here. So people could easily get these two mixed, because one is the row sum, one is the column sum, right? I will tell you one trick to memorize it. The infinity sign is horizontal, so it's the row. And then you will see the 1 is vertical, and then that's the column. This is the things how I memorize the formula. I don't need to memorize the actual number components formula here. I never memorize this, but every time I see it's infinity, and then that's going to do the sum for the row. And then for the 1, and then I'm going to do the sum for the column. That is how I memorize it. Any questions so far? No questions. And let's get back to our starting point. Our starting point is to how to easily to get to know whether we get a convergence iterations methods. So there's one theorem, but we don't want to prove it in this class. We just make use of it. This is not linear algebra class once again. And then we just want to have some things quickly to calculate the things we want. There's one theorem, one very important theorem. It's a theorem on the textbook 7.1.5, but you can double check your lecture notes. And then this is one part of the theorem 7.15 on the type lecture notes. And one important result we want to use is the spectral radius. And then it's smaller than any natural norm A, or any norm of A, for any natural norm A. Which means that either we can use the infinity norm here, or the 1 norm here, or 2 norm here, but I don't tell you how to calculate the 2 norms in a very convenient way, but because outer norm is also difficult to get. You need to calculate the spectral radius again for that one. So I'm not going to mention the outer norm for the matrix. But here, let's say here we have the L1 norm here, and then it could found the spectral radius. And then if we have an infinity norm here, and then we also found the spectral radius. And this is the things. So let's see one example here. Let me give you one very pretty example here. I hope I have one very nice example I can show you. This is not good. I don't have a very nice example at hand, but I can create one. Let's see. Let's say this is a matrix T. I have the matrix T. It looks like 0.5, 0.6, negative 0.5. And then this is the 0.8, and then negative 0.7, and then 0.6, and then 0.3, 0.4, 0.5. And as you can see, it's quickly, you can quickly calculate this. Oh, this is a disaster. No. Actually, I need a sum, right? So I just can create some things looks like this. 3, 2, 1, and then 4, 1, and then 2, and this would not put me into the dangerous situations. 5 and a 1 and 1. And as you can see here, this, if you calculate the infinity norm of this T matrix, and that is the sum of the first row of the absolute value, and then that's 0.6. And the second row is 0.71, the sum. And then the sum of the last one is also 0.71. And this one, you will have the infinity norm is just 0.71. And so for this one, the row T is smaller than or equals to the T infinity norm. And then the T infinity norm is 0.71, which is smaller than 1. And then now you can have, so we can conclude that hence the iterations method xk plus 1 equals to T and then K, Txk. It converges. Does it make sense here? So there's one thing you need to do in the in your homework this week is proving the, let me see, it's asking you to prove the method for a strictly diagonal matrix is convergent. So you might need this. You might need this theorem to help you to calculate the rows. The spectral radius is smaller than 1. You calculate the one norm or infinity norm of the matrix instead, because if you calculate the spectral radius, and then it's not that possible, I believe. So this is one theorem you can make use when you calculate doing the proof for the homework questions. Just one homework question you might need this. And then also you need to go back to see what is the definition of the strictly diagonal matrix. And that's one. Okay, this is an example here. And next, we are going to mention something about so here we already know how when we will have a convergence result. And then there's another things about the convergence. So once we get the convergence result, then people can also prove some more convergence results about this methods. And this is just the first part. And then the second part is the corollary about this theorem. So let me circle out this whole part here in case you cannot see which part from where to where. It's from here to here. This is the theorem part. And then all the things, all the requirement here is just the spectral radius of T. And we also have one things we can use here, that is the theorem 7.115, to decide whether matrix satisfy the row T matrix, row T is smaller than 1. And there's something based on the theorem there, and then that is a corollary of the convergence results. And that's the things below here. So I just say if any matrix natural norms matrix norm is smaller than 1, and then we have a convergence result, and then we prove that, right? Because we can make use of this theorem 7.515 here. And then if the natural matrix norm is smaller than 1, and then which means that the spectral radius is also smaller than 1, which means that we have a convergence result. So I'm just write that down here. So if the natural norm T is smaller than 1 for any, this is for any natural norm. Natural norm, which means that it's defined by the maximum of the AX, maximum of the AX. This is a natural norm, the definition of the natural norms. maximum of the AX among this unit vector space. This is the definition of natural norms. And then, but if any natural norms is smaller than 1, and the C vector is given, and it's a given vector, then the this sequence is converging. K is from the 0 to the infinity. K equals 0 is the initial vector, and then it's defined by this. This sequence is by the iterations mapper, and then it's T xk minus 1, and then plus C. And this sequence is converged. This is the conclusions converges to the solution x equals to Tx, and then plus C. And this is the convergence result, and then this convergence result is for any initial vector. For any initial vector x is 0. We are working on the n-dimensional space. So this is the things, and then all the things is about the norm or about the spectral radius. And actually, we have the area bound as follow. We have the following bound area bounds. And first, so X is a true solution, and the xk vector is the k iterations result in the sequence generations process. And xk is the approximations to the solutions x. And we have an error bound for it, and then that is the T matrix norm, and then to the k order. And this one is the initial vector, and then minus the true solution. And this is the things. And the next, we have x, and then minus the xk. And then it's smaller than or equals to the T, and then K, T norm, and then to the K order, and then 1 minus the T norm. And you will see the denominator is well defined because the T norm is smaller than 1. And here we have the x1 and then minus the x0. So if you take a look at this two area bound, you will see there's something different here. Let's focus on the right-hand side. And on the right-hand side here, this is the difference between the initial guess to the true solution. And yes, this is an error bound. And then you would get your T matrix from the A matrix, right? Because your T matrix is generated by the A matrix. You can decompose the A into the D and the L and the U. And then you have the formula to calculate your T matrix, right? And this is the T matrix. T matrix is from your AX equals to B. But this is the general iteration method. And then you have the T matrix. And then you decide your initial vector. And then this is true solution. And then the question is that maybe you don't know what is your true solution, right? Actually, a lot of time without doing the iteration or solving this equation here, this fixed point problem here, and then you cannot know the iterations, the solutions to the x. So this is just an error bound, and then but we cannot use it when you are doing the algorithm. You cannot say, when we should stop the iteration. But this one is useful because there's nothing about the true solution. This is the first iteration itself. This is the initial guess. And then you also have your T matrix here. And then you can make use of this right-hand side. And then to estimate how big the error you have in the K iteration. And then you let it to be smaller than one number here, and then to control your error. And this one is usable. This one is a good result theoretically, but you cannot make use of it. Does it make sense? Because you need the two solutions here to bound your error. But actually, in the numerical methods, a lot of time you don't know the true solution. That's why you want to use some numerical methods to solve it. But this error bound is pretty useful. Any questions here? The next things, I will keep the next things next time. It's about the SOR methods. It's based on the Gaussian Seidel method, and then we just change something here, and then we get an upgraded version. Because as you can see here, all the things is about the convergence result is about the T matrix, right? And then in the Gaussian Seidel method, Jacobi's methods, and then we calculate the T matrix, and then it's all the things about the A matrix and the D, L, and then U. And if you have the T matrix norm here is smaller, right? Then we would get a better convergence result here. So the question is that could we create a scheme, and then that is better than the Jacobi's method, and then that is also better than the Gaussian Seidel method. And then we just want to find out that such a T matrix, we have a better convergence result. And this is the topic we will cover next week after the Memorial Day on Wednesday. And see you on the Wednesday. I hope you have a happy holiday this weekend. Bye.